All right, THS Chem team, here's your next round of video notes, and this is going to be atomic theory or atomic history. And what we're going to do is introduce quickly the 5 basic atomic models that were created over time up till our present day. So for each one of these, you're going to want to draw a diagram and label all the key important parts that are brought up. And we will actually discuss each one more in depth with activities and in class this week. So here we go. The first one to come up is called the solid sphere, and this is pretty much the simplest model that you can get. This was created by John Dalton, and he was a Quaker back in the 1800s. He was a chemistry teacher, and he used others' experiments. And if you remember anything about Dalton's law of partial pressure from gases, he took a lot of what he learned from the experiments with gases and actually created his own model for the atom. And this was actually the first model that used any sort of scientific backing. And this was around 1803, so over 200 years ago that he created this. And his model is called the solid sphere because that's exactly what it was. Think like a billiard ball or a marble. There was nothing inside of the atom. It was just one solid sphere. And he came up with what are 4 postulates or 4 properties that he said an atom must have. First off, all matter is made of atoms. Atoms are indivisible and indestructible. 2, all atoms of a given element are identical in mass and properties. 3, compounds are formed by a combination of 2 or more different kinds of atoms. And 4, chemical reaction is a rearrangement of atoms. So he started with this, and then as we have gone over time, we've actually disproven 2 of these. So you need to know these postulates, and you need to know which 2 were disproven or are not true today. So first off, number 1, atoms are indivisible, indestructible solids. That is our key there. We know today that there is actually stuff inside the atom. So atoms are not indivisible. They actually have smaller pieces that make them up. So that term indivisible means that there is nothing smaller inside of it. The second one that is not true is that all atoms of a given element are identical in mass and properties. This is also not true because of something called isotopes. So not all atoms of the same element are exactly the same. They're going to differ in their mass. Okay, so both of these are not true. So this was a very simple model that was created by Dalton, and it took a little while for anybody to actually change it, but for the evidence at this point in time, over a couple hundred years ago, this worked out. It didn't change until around 1900, just before, in 1897. Another scientist named J.J. Thomson came along, and he was doing experiments with cathode ray tubes. And cathode ray tubes are basically your old school televisions with the big rear end behind them. They have the big back, and it shoots a beam of particles at the screen. He was experimenting with cathode ray tubes, and he noticed that he could get those cathode rays to actually bend or move depending on if he put a charged plate near it. Because of this, he came up with a hypothesis that the atom itself, which is what the beam or cathode ray was made of, must have smaller particles in it. And it went towards the positive plate, so he said there must be something negative in there. So he said that the atom is still solid, but now it's got these negative particles inside of it. So overall, it's still neutral. It's solid, but now it's got smaller things inside of it. So we get this term plum pudding from a British dessert. And this British dessert, you can think of it like fruitcake. It's bread pudding, and it has plums in it. A more modern way to think about it would be a chocolate chip cookie. So you have your cookie would be the positive substance, and then the chocolate chips would be your negative particles inside of it. Either way, we still have a solid atom at this point in time, right before the 1900s came around. But now we actually have smaller pieces inside of it, and he is given credit for finding the electron. So we now have a subatomic particle at this point in time. The next guy to come along is the first guy to actually find the nucleus. So his model is called the nuclear atom. Sometimes it looks a little bit different than the way it's shown here. You'll think of like Jimmy Neutron, that model of the atom, or the Big Bang Theory when it starts. That is a nuclear atom. And that was discovered by, or created by, Ernest Rutherford. And so this wasn't too far behind J.J. Thomson. This was 1912. And what he did was the gold foil experiment. And we are going to get into detail about this in class and in lab. But in the gold foil experiment, his results led him to two conclusions. First off, nuclear atom, he's the first one to actually find the nucleus. So the nuclear atom has a dense and positive nucleus. And then the electrons are outside the nucleus, hanging out in mostly empty space. So nothingness. And again, we're going to go over in pretty good detail about how Rutherford came up with this atom in class. All right, the fourth one is the planetary model or Bohr model. Sometimes it's even called the solar system model because it looks like the solar system. And this is the most common way we're going to represent the atom. So Niels Bohr is the one that created this model, and he did it right after Rutherford's nuclear atom. So this happened in 1913. Okay, and so what he did is he took Rutherford's model, so we still have basically the nuclear atom, but now notice our electrons aren't just sitting out there randomly, they're in these perfect energy levels. And Bohr used observations based on how different elements give off different colors when energy is applied to them, and came up with the idea that electrons must be found in a specific quantum of energy, and they must have obtained this energy to go between the different energy levels. So the big difference here is that now we have our positive nucleus still, but our electrons are now found in these orbits or energy levels, and they're moving around the nucleus. And our last model, which is going to be our current model, is also called the wave mechanical model or electron cloud model. Instead of having these perfect orbits of energy, the energy is actually in an area or a 3D region called an orbital. So now instead of moving in a perfect circle around the nucleus, these electrons are moving close to the speed of light and moving so fast that they end up having this area that looks cloudy where you can find them. And the darker your area, the more likely it is for you to find an electron there. And so now we don't have orbits, but we have orbitals, which are just areas where you can hold or find two electrons, and think three-dimensional, because we're not going to have a two-dimensional atom. Our atom is actually 3D. And there isn't one scientist that's been given credit for this. This model has evolved over the last 80 years or so, and it keeps changing constantly. So that's why all of this is atomic theory. Everything is still being adjusted or tweaked a little bit. But we still have electrons that are at energy levels. The only difference is that they are now moving three-dimensionally. Now, this is very hard for us to represent or to draw out. So we don't usually use the wave mechanical model when we are going to diagram or draw out an atom. We go back and we use the Bohr model because it's easier to put that two-dimensionally on paper. But some of the scientists that you might see come up in our discussion when we talk about this atomic theory are Schrödinger, de Broglie, Planck, Pauli, and Heisenberg. Again, these are just some of the big names. There's also been many others that have been included in creating this model. All right, so those are the 5 models. Make sure you have an accurate diagram and the basics. Again, we're going to talk about all of these in more detail in class with some activities. If you haven't heard about the Driscoll, go check it out on change.org. Trying to get a new way to measure temperature. Bring any questions to class.